For millennia, across cultures and continents, humanity has gazed up at the night sky, captivated by its mysteries. Are we alone in the universe? It's a question that has echoed through generations, fueling our imaginations and driving our scientific pursuits. Now, after centuries of dreaming and decades of dedicated engineering, our tools have finally caught up with our ambition. We stand on the precipice of discovery, ready to explore the cosmos in unprecedented detail. Enter the James Webb Space Telescope, a testament to human ingenuity and our unwavering quest for knowledge. A gold-plated marvel, its mirrors meticulously crafted to capture the faintest whispers of light from the farthest reaches of space. Positioned a million miles from Earth, far beyond the distorting effects of our atmosphere, it's built to peer deeper into the cosmos than ever before, unraveling the secrets of the universe's origins and the potential for life beyond our planet. Webb's mission, a bold and ambitious undertaking, to look back to the dawn of time, to witness the universe in its infancy, just a few 100 million years after the Big Bang, to witness the birth of galaxies, the swirling clouds of gas and dust coalescing into the majestic structures we observe today, and to scrutinize the atmospheres of distant worlds, searching for the telltale signs of life-supporting conditions. It's not just another telescope, it's a revolutionary instrument. It's a cosmic time machine and celestial detective, capable of peering through the veil of cosmic dust and unlocking the secrets of the universe's past, present, and future. The universe is vast, an almost incomprehensible expanse, hundreds of billions of stars in our galaxy alone, each one potentially harboring its own retinue of planets, and hundreds of billions of galaxies beyond, stretching out to the very edge of the observable universe. Probability suggests life could exist elsewhere, that among this cosmic ocean we are not alone. But suggestion isn't proof. For years we've speculated and theorized, relying on indirect evidence and statistical probabilities. With Webb, we move from speculation to science, from conjecture to concrete data. Observing the faintest glimmers of light from distant stars, measuring the chemical composition of exoplanet atmospheres, and testing our theories against the cold, hard facts of the cosmos. We're not just finding planets, we're characterizing them, we're searching for signs of habitability, for the conditions that could allow life to flourish, for chemical fingerprints that could reveal a biosphere, for the presence of water, oxygen, or other molecules that could indicate the presence of living organisms. The clues are faint, almost imperceptible, photons that have traveled for centuries, even billions of years, across the vast gulfs of space to reach us. But for the first time we have a real chance to answer humanity's oldest question, to determine whether we are truly alone in the universe. The silence of the universe is waiting to be broken, and the James Webb Space Telescope is poised to be the instrument that finally shatters it. The quest to find life beyond Earth is one of humanity's greatest endeavors. To search for life, we need tools that can see the invisible, tools that can reach across vast cosmic distances. Webb sees what our eyes cannot. It possesses a unique ability to perceive the universe in a way that is fundamentally different from anything we've had before. It sees infrared light. The universe is filled with light beyond the visible spectrum, a vast range of electromagnetic radiation that our eyes are simply not equipped to detect. Infrared is cosmic heat vision. It allows us to see the thermal glow of objects in space. Dust clouds hide newborn stars and planets from visible light, obscuring our view of these crucial regions of star formation. But infrared pierces this veil, allowing us to peer into the heart of these stellar nurseries and witness the birth of new worlds. As light from distant objects travels across the expanding universe, it stretches into the infrared, a phenomenon known as redshift. Webb's infrared capabilities are perfectly suited to detect this stretched light, making it our ultimate time machine, allowing us to see the universe as it was billions of years ago. Why does this matter for life? What makes infrared so crucial in the search for extraterrestrial life? Because molecules like water vapor, essential for life as we know it, carbon dioxide, a key component of planetary atmospheres, methane and oxygen, all potential biosignatures, leave unique fingerprints in the infrared. Each molecule absorbs and emits light at specific infrared wavelengths, creating a distinct spectral signature. By tuning into these wavelengths, by analyzing the infrared light emitted or absorbed by exoplanet atmospheres, Webb deciphers the chemical secrets of distant atmospheres, revealing their composition and potentially uncovering signs of life. Its massive mirror, the largest ever sent into space, and advanced spectrographs collect and split this light with unprecedented precision, allowing scientists to identify even the faintest molecular signatures. Unlike Hubble, which primarily observes in visible and ultraviolet light, Webb can study smaller, cooler stars and rocky Earth-sized planets, the most likely candidates for harboring life, which emit most of their light in the infrared. This makes them the best places to look for life. Webb's infrared vision, its ability to see the unseen, is our key to unlocking the mysteries of alien worlds, and potentially to answering the age-old question of whether we are alone in the universe. It's a leap from cataloging planets, simply knowing they exist, to characterizing them, understanding their atmospheres, and searching for the telltale signs of life. The search for life has never been more detailed, more promising, or more within our reach. How does Webb, a telescope millions of miles away, study planets light-years away? It seems like an impossible task, doesn't it? To analyze the faint light from these distant worlds, we need a clever technique, through the transit method. This ingenious method relies on a specific alignment in space. When a planet passes or transits in front of its star from our point of view, it blocks a tiny bit of starlight, creating a subtle shadow. A minuscule temporary dip in the star's brightness. It's like detecting a firefly briefly obscuring a searchlight. This alignment, though fleeting, lets us measure a planet's size and orbit with remarkable accuracy. By analyzing the duration and depth of the dip, we can infer the planet's diameter and how long it takes to circle its star. But the real magic, the true scientific treasure, happens during the transit, in the way light interacts with the planet. A sliver of starlight, like a cosmic key, filters through the planet's atmosphere. This is where the composition of the atmosphere leaves its mark. The atmosphere absorbs specific wavelengths of light, like a sponge soaking up certain colors, imprinting a barcode-like pattern, a unique spectral signature, on the light. This pattern reveals the elements and molecules present in the atmosphere. This is transmission spectroscopy, a powerful technique that unlocks the secrets of exoplanet atmospheres. Our best tool, our most sensitive instrument, for analyzing alien air and searching for signs of habitability. Webb excels at this delicate dance of light and shadow, measuring starlight before, when it's pure and unadulterated during and after a transit, capturing the subtle changes caused by the planet's atmosphere, with incredible precision, far exceeding any previous telescope. By comparing the light before, during, and after the transit, scientists isolate the faint signals, the whispers, from the planet's atmosphere, separating them from the noise of space. For Earth-like planets, small and rocky, these signals are tiny, almost imperceptible. 1 part in 100,000, a needle in a cosmic haystack. Webb's unparalleled sensitivity, its ability to see the faintest glimmers of light, makes these delicate measurements possible. It turns the impossible, the dream of characterizing Earth-like exoplanets, into reality. Each transit, each fleeting shadow, brings us closer to understanding distant worlds and answering the fundamental question, are we alone? Once Webb captures a planet's light, the detective work begins. The data isn't a picture, but a spectrum, a graph of light at thousands of infrared colors. Each peak and valley reveals a molecule: water vapor, methane, carbon dioxide. It's a cosmic barcode, unique to each world. Scientists compare these spectra to computer models, testing countless combinations of gases and conditions. The process is painstaking, requiring hours of observation and careful analysis. Webb has already detected water vapor, sulfur dioxide, carbon dioxide, and methane on various exoplanets. Each discovery refines our understanding of planetary diversity. Some worlds are water-rich, others volcanic, some with clouds of sand. Every spectrum brings us closer to finding a world that chemically resembles home. The search is a puzzle, each piece a step toward answering the ultimate question. Finding the right atmospheric mix is just one part of the puzzle. Habitability depends on a planet's atmosphere, surface, interior, and its star. Many exoplanets orbit red dwarfs, stars prone to violent flares that can strip atmospheres. A planet's geology, volcanoes, tectonics, regulates climate and recycles vital chemicals. Webb can't see surfaces, but atmospheric clues hint at geology. Confirming habitability requires knowing a planet's mass, density, star activity, and climate. The search is a marathon, with Webb leading a global team to build a complete picture. What are we really searching for? Biosignatures, chemical clues that require life to exist. On Earth, life transformed our atmosphere, filling it with oxygen and methane. Finding both gases together on another world would be a powerful hint, since they destroy each other and must be constantly replenished. But nature can create false positives. Geology or star chemistry can mimic life signals. That's why context is everything. A single gas isn't proof. Scientists look for combinations of gases in disequilibrium, mixes that shouldn't exist without life. If Webb detects a potential biosignature, the work intensifies. Every non-biological explanation must be ruled out. Follow-up observations and rigorous modeling are essential. The bar for claiming life is extraordinarily high. Only overwhelming evidence will do. For decades we searched for another Earth, but what if life thrives on worlds unlike our own? Enter Hycean planets, hypothetical worlds with deep oceans beneath hydrogen-rich atmospheres. These super-Earths or mini-Neptunes could have broader habitable zones than Earth-like planets. They're common in the galaxy and easier for Webb to study, thanks to their thick atmospheres. If Hycean worlds exist, the number of potentially habitable planets could be far greater than we imagined. The idea is new and unproven but electrifying. It challenges us to think beyond our own planet's limits. Webb is the perfect tool to test this bold hypothesis. To test the Hycean idea, we turn to K218b, a mini-Neptune in its star's habitable zone, 120 light-years away. Webb's observations revealed water vapor, methane and carbon dioxide in its atmosphere. The lack of ammonia hints at a possible ocean beneath the hydrogen-rich air. Even more intriguing, a tentative signal of dimethyl sulfide or DMS, a gas produced by life in Earth's oceans. If confirmed, DMS would be a tantalizing biosignature. But caution is key. The detection is tentative and must be verified. Scientists must rule out non-biological sources and confirm the signal's reality. K218b isn't a confirmed ocean world or inhabited planet, yet, but it's a spectacular laboratory pushing the boundaries of what we can know. The James Webb Space Telescope is a trailblazer for astrobiology. Every observation, positive or negative, refines our search and guides future missions. Webb's data is shaping the design of next-generation telescopes, like NASA's Habitable Worlds Observatory. Its discoveries inspire and unite us, reminding us of our place in the cosmos. The search for life is just beginning. Webb is our flagship, charting the way to new worlds. The journey is long, but the destination is finally within reach. The cosmic story continues, and we're living its most exciting chapter yet.